Okay, let's unpack this. Imagine you've got this piece of software, right? Something really critical, and then suddenly, bam, it just won't compile with the modern tools. It's like hitting a brick wall. That's kind of the challenge we're diving into today. There's this report, Havoc C2 V8 Diamond is unbreakable.
Oh,
And our mission really is to understand how version 7 of Havoc C2, that's an open source C2 framework, for security testing, how its daemon payload specifically ran into this wall.
right. And it's fascinating because it wasn't one big obvious bug.
No.
No, it was more about these subtle sort of hidden assumptions in the code clashing with newer, stricter compilers.
Yeah.
Providing things like incompatible pointer types or errors about mixing integers and pointers during
I like
initialization.
that to sound like compiler messages. Yeah. I see references here to issues like hashtag 533, hashtag 553, hashtag 563. So users were definitely hitting this.
They were, yeah, across different setups too. And the really interesting part, like you said, is how they fixed it. A really precise, almost surgical patch. It got things working again, but, and this is key, without actually changing what the payload did.
Okay, so it fixed the build without altering the behavior. That's the goal, usually. And we want to understand why these small technical things mattered so much and how just the right fix can, well, save the day.
Exactly. And the root cause, like I mentioned, wasn't sudden. It was this gradual evolution of the tools. TCC Clang, Mingu W6. That it just got much stricter. The daemon payloads code, you see, was deeply tied to low-level Windows implementation details.
Like what specifically?
Things like directly reading data structures like the thread information block, the TIB.
Right, at the tip,
Yeah.
builds thread info.
Yeah, or doing raw FS segment reads to get at specific memory locations. And it also had to handle wild W64 transitions.
That's the 32-bit on 64-bit Windows compatibility layer. Right.
Exactly. So code that used to work, maybe making assumptions about converting between integers and pointers. Well, the stricter compilers started flagging that. Hard errors or warnings treated as errors.
So it's like the coding rulebook got updated, and what used to be okay, maybe a bit sloppy, but okay, now just breaks the build.
Pretty much. Those symptoms, the integer pointer initialization warnings, the incompatible pointer types, they were blocking compilation for people. Those issues you mentioned, hashtag 533 and the others, they showed exactly that.
Okay, so how did they track down the exact lines of code causing the trouble? It sounds like it could have been anywhere, almost.
Well, it really highlights this broader thing in software, right? These implicit assumptions in older code bases. They can become super fragile when the environment changes. The investigation eventually zeroed in on how memory addresses and data types were being handled, specifically in a file called syscalls.c.
Just skulls.c. Okay.
Yeah, particularly in the code paths dealing with that WowW64 layer we talked about. They found places where 32-bit values read directly from system memory were being just assigned straight into pointer variables.
Ah, I see. And a modern 64-bit compiler would look at that and say, hold on, a 32-bit number isn't necessarily a full 64-bit pointer address.
Exactly. It's a dangerous assumption. The compiler sees a potential mismatch,
Mm.
maybe data loss or incorrect addressing. It's trying to prevent bugs.
Right. Trying to fit, well, maybe not a square peg in a round hole, but maybe a small peg in a big hole where it expects a perfect fit now.
That's a good way to put it. And the fix, this is where the diamond is unbreakable name comes in, it was incredibly precise.
How so?
Instead of the direct assignment, they used explicit pointer casts. The project had a macro, CPTR. They wrapped the 32-bit value in that. It basically tells the compiler, look, I know this is a 32-bit value right now, but I explicitly intend for you to treat it as a pointer here.
So making the intention explicit, documenting it right in the code, and satisfying the compiler's need for clarity.
Precisely. It handled the conversion correctly, turning that 32-bit value into a proper pointer-sized variable for the system, and silenced those really nasty compiler warnings.
That makes sense for syscalls.c. You mentioned it was surgical, though. Were there other spots?
There were, yeah. Another key fix was in thread.c, specifically in a function called threadCreateWowW64.
Okay, thread.c. What was the issue there?
It was a bit similar, involved passing pointers around, but in the context of something called a thunk.
A thunk. Like a little adapter code.
Yeah, essentially. It's a small piece of code used here to execute 64-bit code from the 32-bit WowW64 process. The issue was passing a context, which was pointer typed, into this thunk. The thunk itself expected a 32-bit integer parameter according to the system rules, the ABI. The original code just sort of assumed the pointer would fit or be handled implicitly.
Another implicit assumption biting them back. So how did they fix that one?
Again, with explicit casting, the fix was at line 186. It changed how the parameter was passed. Instead of just passing the address at sectx, it became dword, UPT, etc.
Okay, break that down. UPTR first.
All right, UPTR is another project macro, likely converting the pointer to an unsigned integer type suitable for holding an address. Then, crucially, it casts that result explicitly to dword.
Dword being a 32-bit unsigned integer type in Windows terminology.
Exactly. So that explicit truncation to dword made it precisely match what the system's calling rules, the application binary interface, expected for that thunk parameter. No more ambiguity.
And that cleared up those specific compiler errors, like Wnt conversion and Imineclu Win-compatible pointer types.
Yes, exactly. And again, critically, it didn't change the logic. The control flow, the security implications, none of that was altered. It just made the existing assumptions explicit for the modern compiler.
It really is quite elegant when you see it laid out. Just a few very targeted changes, making implicit things explicit, solving these build-breaking issues. This diamond is UnBreakable fix. It definitely offers some powerful lessons.